All right, so this is Horner again. We're going to look at section 20.2, electric generators, and this is great to go right after the motional EMF because in a generator, what we're doing is we have a magnet. So you'll notice that we have two magnets. We have a north and a south side here, therefore we generate a magnetic field across this coil. So there's our coil, but this coil is a little bit different than the coil that we had before. The other coil was just sliding, if we remember. We were sliding that across a magnetic field, so it was going in this direction. This coil is different. This coil is actually fixed on an axis, so you'll see the axis, and you'll notice that it rotates. So this side might come up while side number 4 is going down. And as it does that, it's going to cross through the magnetic field. That generates a current in this, and because one's going down, one's going up, it does make the current go in a certain direction, and therefore you'll get that that generator will produce electricity or produce that current as it goes through from the potential difference that's generated. So in order to do this, you'll see that side 1, side 2, side 3, and side 4 are here. So none of the 4 sides of the loop move perpendicularly to the magnetic field at all times. So we're going to have to generalize the results that we had in that first section. In problem 67, which I don't think we're going to do, we could verify there's 0 EMF in sides 1 and 3. So we're really going to just concentrate on 2 and 4. You'll notice that these are the electric field lines are parallel to side 1 and 3, and then they're perpendicular to 2 and 4. So we're really going to focus on sides 2 and 4. Since they don't really move perpendicularly to the magnetic field, the magnitude of the average force on the electrons is reduced by a factor of the sine of the angle. So where that sine of the angle between the velocity of the wire and the magnetic field gives you this force. So the average force here is the elemental charge times the velocity times the magnetic field times the sine of the angle. And so that's what we'll kind of discover as we go through. The induced EMF is then reduced by that same factor, so that'd be VVL sine of the angle because of the angle there. And that induced EMF is proportional to the component of the velocity that is perpendicular to the magnetic field. So here we've got the perpendicular velocity is V sine of the angle. So for just some sort of visual image to help for you to think about it, we can think of the induced EMF as something that is proportional to the rate at which the wire cuts through that magnetic field. Okay, so it only does it at certain times, and there's a component of the velocity parallel to the magnetic field that moves the wire along the magnetic field lines, and so that doesn't contribute to the rate at which that wire cuts through the fields. So you could kind of think about this as, let's say I have a block of cheese. And whenever you cut a block of cheese with a cheese cutter, you know that that wire that goes across will come straight down through the block. Then when you pull it through, once it gets out of this cheese block, it's not cutting it anymore. You have to lift it back up and then take it down through again. So if you think about that, that's what's happening, but it's actually doing it kind of at an angle. So as it cuts through it, that's where the sine of the angle is actually coming from. So it's a little bit different. I'm going to pull later I've got a good FET that will go through and kind of help you. It's a visual, one of those virtual labs that you can take a look at. So the loop turns at a constant angular speed, so that's omega. So the speed of sides 2 and 4 is actually, this is linear speed, is equal to the angular speed times the radius. So that'd be from that point that you're turning at all the way out to the edge of where the wire is. That angle does change at a constant rate of the angular velocity or the angular frequency, which is the same thing. So we're going to choose the angle is equal to 0 at time equals 0, so that our angle is equal to omega t, and that the EMF is a function of time in sides 2 and 4 will be the equation that we have down here. So remember, we want, this is our linear velocity, and we're just going to change it to angular velocity. And when we do that, then we can also say that's the frequency times the time here, instead of having the angle itself, since we said that the angle is frequency times time in this little derivation of the equation here. So good picture of kind of show you what's happening. So sides 2 and 4. So we're looking at it from the edge, move in opposite direction. So current does flow in opposite directions. In side 2, the current flows into the page. So we're saying that the current is flowing in this direction. And when in side 4, it's moving out of the page, so it's coming towards you. So we're going to do our X circle and our dot circle. Notice that this angle as it moves through does change, okay, until you get to this configuration, and now you'll see that it's in line with the field. Here, this is the angle between the velocity and the magnetic field, and here you'll see that the velocity and magnetic field are perpendicular. So that shows you just 3 different situations that the motor is going to be in as it rotates through. So both sides tend to send current counterclockwise around the loop as we look at it in the figure. So the total EMF is actually the sum. So we're going to have to say 2 times that angular frequency times the radius times the magnetic field times the length of that side times the sine of omega t. And the rectangular loop does have sides L and 2R, so the area of the loop is 2RL. So the total EMF as a function of time is going to be the equation that you see here. So it's omega BA times the sine of omega t. You can't take these and factor out that omega. It doesn't work that way because here we're doing the sine of that function there, which is really important to recognize. Okay, so if we write it in terms of the area of the loop, this would be good for any planar loop of any shape. So you can have that loop, and by planar they mean it's flat. We can have it of any shape. So if the coil consists of a lot of different turns of wire, then that EMF is N times as great. So you'll notice that whenever we have a generator, that generator will, instead of just having one wire that comes in and does like this and then rotates through, we actually will have it so that we have a lot of loops. So there's 2 loops, 3 loops, 4 loops, and every time I add that, I can multiply the EMF by that N times. So you'll notice that now in our equation, we've placed an N where we didn't have one before, and that just multiplies the EMF by the number of loops. So the more loops you have, the more potential you can generate, which is a good thing for a generator. Makes it pretty efficient as it works through. The EMF that's produced by a generator is not constant. It is a sinusoidal function, so it goes from positive to 0 to negative, and then to 0 and then positive. And the maximum EMF here, which is E omega times the number of coils times the magnetic field times the area, is called the amplitude of the EMF. And that's just like in simple harmonic motion. So from here down to the 0 line is our amplitude. For the next slide here, the application we have is for a DC generator. This is one where the EMF does not reverse direction. So one way to make this DC generator is to equip an AC generator with something that we call a split ring commutator and brushes, exactly as we do for a DC motor, and that was in section 19.7. So just as that EMF is about to change direction, the connections are switched, and so instead of getting the graph that we were getting before where it was going up and all the way down and then back up again, which is really alternating current, we're going to end up with this thing where it will continually go positive. So this will make sure that we do have a DC current going through. Okay, and you'll notice that it does vary and it does cycle through as it goes through. So this is the equation we can use. We've done the absolute value now of the sine omega t because we are only seeing positive values here. More sophisticated DC generators have many coils distributed evenly around that axis, so that EMF in each coil varies a little bit, but as each coil reaches its peak EMF at a different time, we get a pretty constant DC voltage as it goes through. And then therefore it really just has small fluctuations. We can use a regulator to keep that pretty constant. So in example 22, here we have a simple DC generator. It's in contact with a bicycle tire, and it generates power for a headlight. The generator has 150 turns, so there's our N value of wire. It's in a circular coil, so it doesn't have to be a box coil like this. It can actually be a circular coil. It would look like this. Um, the radius of that coil is 1.8 centimeters, and then the magnetic field strength in the region of the coil is about 0.2 Tesla. When the generator supplies an EMF of about 4.2 volts to the light bulb consumes an average power of 6 watts and a maximum instantaneous power of about 12 watts. So those are some things we know about that. They want to know what's the rotational speed in RPM of the armature of the generator, so that's the part that's spinning. They want to know what's the average torque and maximum instantaneous torque that's applied by this bicycle tire to the generator, assuming that that generator doesn't really lose anything, and therefore we call it ideal. And if the radius of the tire is 32 centimeters and the radius of the shaft of the generator where it contacts is about a centimeter, they want to know what is the linear speed that the bicycle must move to supply an amplitude of 4.2 volts. So we want an EMF of about 4.2 to run it. So for letter A, here's our basic equation. We'll see that the sine of omega t does drop out. And so here we have E of M is just omega NBA. We know the turns was 150. We know the number of terms is 150. The area is pi r squared, and the magnetic field is 0.2 Tesla. So at this point, we need to find out what is this angular frequency or angular speed. So we plug in our numbers. We've got 4.2 volts for that maximum EMF. 150 is the turns, pi r squared times 0.2, which is the magnetic field strength, and you end up with 137.5 radians per second. If we want to convert that to RPM, that tells you how many revolutions per minute that it's turning, and that's typically something a little bit better understood in the world of thinking about things rotating. For letter B, we know power is equal to work over time. That's also equal to torque times the change in the angle over the change in time, so that's just torque times the angular velocity or angular speed. So here we've got the average power divided by the angular speed is equal to the torque. So we end up with 0.44 newtons times a meter because we know that we had 6 watts of power. There's that 137 radians per second we got in A. If you do the maximum power, which would be 12 watts, then you've got a torque on that wire of about 0.087 newtons times a meter. For letter C, here we've got the velocity, and remember it's just omega r, so we're just going to multiply that omega, which is that angular velocity, times 0.01 meters, and you get 1.4 meters per second, and that's assuming that the bicycle rolls without slipping on the road. And its linear speed is about 1.4 meters per second. So that means that our bicycle, here's our bicycle, handlebars here, and we've got our person sitting on it. It is moving in this direction at 1.4 meters per second, and the tire is rotating at 137.5 radians per second. Okay, and that is example 22. The next section we'll do is Faraday's law, which is 20.3.